All right, guys. So we're going to move on to the next chapter, which is actually going to be chapter 9, Meteorology. It's going to be the theme, and we're actually going to learn a little bit more about the atmosphere, and specifically, we're going to look at winds, we're going to look at fronts, and kind of get a sense of where some of these storms and different things come from. So to frame that, let's look at a quick overview. All right, we're going to see causes of weather, weather systems, gathering weather data, and then weather analysis and predictions. All right, so these notes can be found in with this assignment, so go ahead and open those up, hot off the press. Just finished them up for you guys, and now I'm going to use these over the next 3 days to get you guys going. All right, so if at any point in time you need to, feel free to just hit pause, fill in whatever notes you need. I'm just going to keep going, so you guys have control over the tempo of the class, and if you need to rewind, fill anything in. Any questions that come up, maybe write them on your notes so that when I'm in on Thursday, I'm going to start by recapping on this stuff, and if you guys can ask me your questions then, we should be able to lock this in. All right, you will have homework tonight, and I am checking that it gets turned in. All right, so let's get into this. How do satellites help us track and predict weather? So in the exosphere, which we learned about, that transitional area between our atmosphere and space, we have approximately 7,000 satellites that are orbiting the Earth. And some of them are actually able to use radar and basically send down beams of energy and then have it bounce back and be able to detect water in the atmosphere, water levels, energy, things like that. And from that, we see in our satellite images when we watch the news, or if you want to see a weather forecast, they can actually be able to see where there's clusters of energy, where there's different pressures. And by knowing what those different clusters are, you then can understand what type of weather is associated with that. So we're going to look at that. We're going to look at some air masses, and let's have some fun. So first up, causes of weather. Right? And the focus question, how does heat drive weather? So let's first define heat. And down here we have the definition for heat, the transfer of thermal energy from a warmer material to a cooler material. I like to think about heat as a measure of the amount of energy. A measure of the amount of energy. So I'm going to take the textbook definition. I'm going to put my own spin on that. And to help you guys to understand that, and then we'll come back to heat in the atmosphere, I like to think about a glass, right? If I have my coffee cup, right? So there's my little coffee cup. And I have about 12 ounces of coffee in my coffee cup. And the temperature in there is 140 degrees. This is going to be Fahrenheit, by the way, if you're guessing, right? And then if I have a bathtub, right, so we're going to make a little bathtub over here, right? Bathtub usually has that little like spout thing over here with like little knobbies, right? If I have a big old bathtub, right, and this now has, rather than 12 ounces of water, let's say I have 70 gallons of water. And if the 70 gallons of water are, say, what's a nice bath water temperature? Let's say it's 88 degrees Fahrenheit. We can see that the temperature, right, the temperature over here is in fact actually higher, right? So we would say this is a higher temp. But there is more heat in the bathtub. And the reason being is that there's more water over here that has more energy, right? So it's the total amount of energy when we're discussing heat versus temperature. But now how does that relate back to Our atmosphere. Right? So how does heat drive weather? Well, when we have a buildup of that thermal energy, that's where we can have areas that have that low pressure, right? And remember we said that when we have warm air, right, or a whole area that's really warm, we're going to get a lot of rising air, right? And that rising air later on can lead to things like condensation and then precipitation. We can also have areas that maybe get less sunlight, right? And we end up with colder areas. And we know that colder areas will then have more sinking air, right? And this then becomes our high pressure. Over here we have our low pressure, right? And the high, we said, will make high winds go to, or the winds are going to be the result of the high pressure to low pressure. Well, on Earth's surface, when we have these imbalances of heat then driving evaporation, or the absence of heat causing this condensation and cooler areas, we're going to see how we can get convective panels, and also how this imbalance can cause global winds. So all of this together brings in different types of weather. Now, just to frame this, Saturday morning, I woke up to go to Science Olympiad, and the thermometer on my car said that it was 7 degrees Fahrenheit. Now, I thought that was pretty cold, right? And I'm not like big on using hot and cold, but I was like, okay, you know what? Yeah, this is a little cold. When I got home that night, right, so in the morning, I'm just going to put some notes up here. In the morning, it was 7 degrees Fahrenheit. In the evening, it was 22 degrees Fahrenheit, right? I got home, it was late, it was dark. Ironically, they were both dark. But 22 degrees. When I woke up on Sunday morning, right? So we're going to put Sunday over here, right? I had to come up here to the Army, and it was 33 degrees Fahrenheit. Now I'm pausing for you guys to process this for a second. It was dark here, right? So the happy little sun was out over here. Over here, this is all dark, right? Let's shade this whole area. This whole area in here was all kinds of dark. How did the temperature increase 11 degrees Fahrenheit? And the answer there is the winds. The winds brought in a different air mass, which then brought warmer air into the area. So heat, driving weather, is more than just sunlight, right? That's the theme that I want to really get you guys focused with. So, vocab we'll get to. As I said, little reference back to heat. Now, let's talk about meteorology. First off, a meteorologist is the person that gets on the television and predicts what the weather is. That's an actual program that you go to school for, just like geology or biology. A meteorologist is going to study the atmospheric phenomenon. So meteorology, study of the atmospheric phenomenon. The meteorologist is the person. Now you got the Greek breakdown on this, but we're just going to keep rolling. Short-term variation of the atmospheric phenomenon that interact and affect the environment on Earth are called weather. So all these short-term variables, higher temperature, lower temperature, strong winds, cloudy, high wind speeds, all these different things, all these variables are going to affect in short term what you're experiencing in your immediate area. So that's what we refer to as atmospheric phenomenon, right? Even if I have a thunderstorm that comes rushing in, well, okay, initially high winds, lightning, but then there's probably going to be colder temperatures that follow. The humidity is going to change. All of these variables are simply temporary. When we discuss long-term what variables are going on, when we look at the average over a long period of time, that's where we get climate. And I like to say that climate is what you expect, weather is what you get. That's how I differentiate between the two, right? And I always tell people that I went to Hawaii for 12 days. when I was in Hawaii, I expected paradise, right? The climate for Hawaii was going to be paradise. It was going to be 70 to 80 degrees, right? It was going to be sunny. It was going to be beautiful, no rain. Everything was perfect. And 11 days of my time in Hawaii were exactly what the climate had predicted. It was amazing. But one day, for 4 hours, I was driving through some crazy rain. I was driving around the north side of the big island of Hawaii with a rain shadow effect, which, remember, we talked about orographic lifting. So orographic lifting was causing heavy precipitation on the north side for 4 hours as I drove around. And then when I got to the south side, it was desert. It was super dry and super hot. But my point there is the weather is what I actually got. It wasn't what I expected, right? And we describe climate when you look at a pattern over decades. That's a really long time. Decade, again, 10 years, right? So if we say decades, we're talking 20, 30, 40 years. You add all of those up, right? 365, go ahead and multiply it out. You're talking a lot of days. What's the average temperature? What's the average rainfall? What's the average winds? Right? You put all those different things, and that's how you get a climate. Okay, I think I've belabored that. Now, the fun part here is when we think about the temperature change on the Earth. And really, by the way, I'm just going to say, when thinking Christmas right now, so I'm going to make it red. And we have the reason for the season. Right? Not only this slide is talking about, and you guys are going to fill it in, right? Not only is it talking about Earth's axis of rotation being tilted, causing a temperature difference throughout the year, but that's really the reason why we have seasons. There's a time in the year when Earth is tilted toward the sun. I'm drawing in highlighter now, that's great. And 6 months later, Earth's axis is tilted away from the sun. Right? And for those of you who are like, I'm not really understanding what he's drawing right here. Right? So we, right now, this is December for us. Right? We, in the northern hemisphere, are tilted away from the sun. So there's the North Pole and there's the South Pole. And 6 months later, this is going to be the North Pole. That's going to be the South Pole. And when we're tilted, the angle of insolation is going to be higher in the North Pole. It's really shining toward the whole northern hemisphere up in here, right? So you're going to get a lot more heating. Over here, you can see that it's tilted away. So there's a lot more heating in the southern region, and therefore it's going to be colder up here. When I am with you on Thursday, I will draw this whole thing out on the board, so please do not hit the panic button right now. I need like the entire whiteboard to go through all the wonderful things that make seasons. One of my favorite topics in earth science to explain to students, but it's got to be on a big board, and I need all my different markers. So I'm just giving you guys a little glimpse as to where we're going. Right now, let's get back to the notes and the fact that the notes say one reason that temperatures may vary from location to location at a certain time of year is the Earth's axis of rotation is tilted. Now, Earth's axis, this is super important. The axis is tilted at 23.5 degrees. That tilt is what we were just looking at here. There's an angle between the Earth's axis and where it should be at a true 90. So that's the little angle in here that we're looking at, right? Again, I'll get into a little more detail, just giving you guys an overview on that. Definitely a testable topic, though, so stay tuned. It's going to get fun. So here we can see that the angle of insolation is going to be changing, right? Here they call it the angle of incidence of sunlight. But basically, what that's really talking about, if you focus in over here, right, here there's a lower angle, which actually spreads out the light over a given area. And I'll demo this with a flashlight with you guys on Thursday. Right? If the flashlight is dead on 90 degrees, and you can see that 90-degree angle right here, 90 degrees, you have a very, very focused and concentrated beam of light. Right? If the end of my flashlight is 1 inch in diameter, or the diameter of a quarter, well then the circle that's going to be shown down on or illuminated is going to be 1 inch in diameter. But if I lower that angle, right, and I come up to the top up here, right, that angle now, because there's an angle, it's going to spread that light or that energy over a larger area. And if you think the last time you used a flashlight, maybe you were walking along, I know with the scouts when we go hiking, they like to take their flashlights, which is ridiculous. I like to turn off the lights and use our night vision, the stars, but whatever. Let them use their flashlights. Probably better they don't trip. But think about it. You're holding a flashlight at the side, and it's out in front of you. It's shining over a very large area. It's spreading that light over a large area. And so the sunlight, when the angle is coming in, as you see up here on the top, when it's spread over a larger area, it's less concentrated. And so the less concentrated, the lower the temperature for a specific spot will be. When it's more concentrated, like you see down at the bottom, it's going to be more intense, greater concentration. All right. I'm hoping that sort of helps. The reading should certainly help. And then the questions you guys are going to do tonight hopefully reinforce that as well. But I'm going to keep going. Let's take a look here. So if the concentration of energy wasn't bad enough, Earth is also rotating, and the air that's moving, remember the high pressure to low pressure, there's a constant churning, which is then going to redistribute that energy around the Earth. So think about when you have food, and you're like, oh, it's fresh out the oven, or maybe you just got a slice of pizza from the pizzeria, and it just comes out the oven, comes down. If you go and take a bite of that, you're going to have that hot cheese burn the whole inside of your mouth. It's going to be very painful. Instead, what do we do with it? I think, what do? You get a hot slice of pizza. What do? If you're like me, you go and you blow on it, right? What are you trying to do? You're trying to redistribute some of that heat energy. You're trying to cool it off. Well, the Earth has a natural cooling off effect just by the blowing of wind, right? By that circulating of energy. You're redistributing. You're taking some of that warmer air and moving it somewhere else, and you're adding some of the cooler air from you over that hot surface. If we tie that back to my opening statement about Saturday versus Sunday, some of that warmer air that was being blown off one area pushed into our area, and that's why when we woke up Sunday morning, it was warmer out than when we went to bed on Saturday night. And that sets us up to understand what an air mass is. So an air mass is a large volume of air that has the same characteristic such as humidity and temperature. Now, an air mass forms over a source region, which means there's going to be a specific area where air masses tend to form. And we're going to focus on air masses that form over warm ocean, cold ocean, warm land, cold land, and the Arctic. All right, so there's going to be 5 different air masses that we're going to look at. And if you're sitting there going, wait, I got to write all of these down, don't worry. They're in the slides to come, right? But we're going to be looking at 5 air masses. And I'm going to tell you right now, definite test diagram. All right, so when the time comes that we go through all this, make sure you're thinking, I got to know all my air masses. I better not just memorize definitions. All right, let's keep going. So the first one we start to think about, right, the origins of marine tropical air masses. Meaning marine over the water, right? So that's probably going to give us some humidity. And then tropical, when I think tropical, I think warm, right? So if I've got warm and I've got moist, I've got perfect characteristics for a marine tropical, or what we call an MT air mass, maritime tropical. Right? And I know I'm saying marine maritime because I was trying to get you guys to link the two. Right? Mariners, people that work the ocean, the sea. Good. So right here you had to fill that in. Hot, humid, moist. Right? When we think moist, humid, hopefully those are synonyms now for you. And then we got some reference here. Southwestern United States and Mexico are the source region for a continental tropical. So this is continent, we're thinking land, which is probably going to be dry, right? And then tropical is also going to be warm / hot. So this, I'm going to change the color, right? This over here is going to be continental tropical. When I see C and T, I know dry and warm. Again, just to recap, when I see marine tropical, I'm thinking moist and warm. Sorry if I'm scribbling all over the things you guys need to be able to see. You can always rewind. All right, now let's kick it up a notch. Let's go from the warmer tropical Caribbean, great place to go right now, right? It's be super warm. Well, let's think, where are we right now, right? We're in more of the maritime polar. As we come to higher and higher latitudes, maybe you want to go up to Maine for the weekend and go out on one of those boats that are crazy cold, those guys. They're a real feat what they do. But they're out on the open ocean, and the air mass that would be forming up there is going to be cold, but it's also going to be moist. All right? So, cold, moist is going to be our maritime polar. Right? I drew that in reverse. I apologize. Right? So, moist and cold. If we go over the land, though, again, let's go with the green for land. So continental polar is going to be dry and cold. So I told you 2 slides ago that there were going to be 5 different air masses. I just gave you 4 of the 5. The last one is an Arctic air mass. And an Arctic air mass, if you think about going up into the high latitudes, up into the Arctic Circle, it's going to be dry, but it's going to be super cold. Super cold. So you got cold with polar, think super cold, icy, snow-covered surfaces, Siberia, Arctic Basin, right? Those are great examples of an Arctic air mass. That's just going to be an A. Okay, so it has its own little category, but that's why it gets a single letter. Pretty easy to understand. Now, if you're sitting there going, wow, you just threw a whole lot at us, Mr. Weavers. How are we supposed to ever remember that? I'm a nice guy, right? There's a little chart for you. So, gives you source region examples, right? So, source region examples. Gives you the letters that you're going to need for a map. Gives you a description of what you got. And then, this is what it's going to look like in the winter. This is going to be what it's looking like in the summer. But generally, everything I just wrote for you, you can get a breakdown on that. So I hope that helps you guys to understand air masses and where some of these conditions are coming from. Because when we have these air masses push into our area, we know what type of weather we can expect to get. But now let's understand something. When that air mass starts to move over land or water that has characteristics that are a little bit different, the air mass starts to acquire or basically undergo change, right? So air masses aren't just set, right? They can start to dissipate. They can start to get new characteristics over time. And that's a pretty cool thing, but it also then explains why weather is in constant state of flux, why there's constant changing of the atmosphere. And now the last slide for today we're going to look at right here talks about the lake effect snow. So one of my buddies up here is from the Syracuse area, right? Go Orangemen. So Syracuse is known for lake effect snow. So they've got some of the Great Lakes up north in New York State, and what happens is when the air moves across the Great Lakes, there's getting a lot of evaporation off the water, but the air above is cold, right? And just to loop it back here, right, you guys can actually see right here that you have a continental polar air mass. We said continental polar is going to be cold and dry, but now I'm getting moisture. I'm picking up the moisture from the water below. And so we already know from our last chapter that cold air holds less water than warm air. So you basically build up these clouds, and then when you get to the other side, you end up getting that precipitation. But that precipitation in the winter months can be very large accumulations of snow. So if you pay attention to the news and you see where the snow's been going, over the last 2 weeks, upstate New York has got hammered with some heavy, heavy snow. Back in December, the Buffalo, Rochester area, hammered with snow. This is lake effect snow. And it's explaining where some of these different phenomena are coming from. So if you like snow, if you want to see what 4 feet of snow is like, 6 feet of snow, great places to go and move. Right? You go up into, and some areas are really known for some heavy snowfall. The cool part is they have the equipment and the experience to handle snow like that. Right? When an area is prone to a certain type of condition, the local government equips themselves to be able to take care of the people. Whereas if you go down to Florida, you're not going to find snow plows and salting trucks because that's not something that they often have. When Florida gets snow, like everything stops, and people walk outside with brooms because they don't know what to do. And that's not their fault. It's very infrequent that they ever get snow. So just kind of cool. Ties earth science back to a couple different things that are going on in our daily lives. All right, at this time, I'm going to stop the video. If you guys need to go back and catch anything, take a few minutes, fill in whatever notes, and then go ahead and start your homework. And I'll talk to you guys tomorrow. Thank you.